get familiar. So if you don't know by now, then you should probably get familiar.
Hello students, so welcome back to the video part number 7, I think, right? Okay, now in this part of the video, as I told, I am going to discuss the growth of charge in a RC circuit. Okay, so that means we are considering a circuit in which the resistor and capacitor are connected in series. Okay, so that means this series combination of RC should be connected to a DC source, so with a tap key. Okay, so in this circuit arrangement, so one can charge the capacitor the moment you press the key. Okay, that means if you press the key, the circuit is closed. If you open the key, then circuit is open. So that means to charge the capacitor, you have to press the key. In order to discharge the capacitor, you have to open the key. So that is the arrangement in the circuit here. Okay, now look at the point here. When the key K is closed, okay, the moment you press the key, it is closed. The capacitor starts charging. Okay, it starts charging up, and charging current, whatever the current it is passing through in the circuit is called charging current. Okay, so the charging current is maximum due to entire voltage drop across the resistor R. Okay, what do you mean by that? So the moment you press the key, so the charging current is maximum because there is a voltage drop across only R. Okay, entire voltage drop takes place only at the resistor R, because initially there are no charges in the capacitor. You have to assume that capacitor is not consisting of any charges in it. Okay, so what is the role of capacitor? Capacitor is the device which can store the charges in it. Okay, so the moment you pass the current, it starts charging. What do you mean by that? It starts accumulating the charges in the capacitor. So initially number of charges in the capacitor is 0. Okay, so Q is equal to 0 in the beginning. So at that time, what is the current? Current is said to be maximum. Okay, because of the potential drop across only R. Okay, once the capacitor is completely charged, so Q is maximum. Okay, so when the Q is maximum, the current is minimum, so that one can have the voltage drop from the capacitor. Okay, that is called discharging of the capacitor, right? So I am considering at the time t equal to 0, so Q is equal to 0 here. So at that time, the charging current is maximum in the circuit, and potential drop across the resistor is also maximum. Okay, now what is the initial charging current then? So that initial charging current when time t equal to 0, okay, Q equal to 0, the maximum current is said to be I naught. So I naught is equal to E by R only, because whatever the potential obtained from the supply E, okay, it is obtained across the resistor R. So from the Ohm's law, I is equal to E by R. Okay, just like V by R itself, it is E by R. Okay, now at any instant, let the charging current. So now as you increase the as you just wait for the time, okay, with respect to time period, the current is varying. So that variable current is said to be I is equal to dq by dt. So this dq by dt is nothing but what? Rate of change of charges. Okay, so the rate of flow of charges can be considered as the current. So that is the variable current at any other instant except at time t equal to 0. At other all instants of time t, the current is considered as dq by dt. Okay, now the question is growth. How this current is increasing? It is growth, isn't it? So to observe that the growth of the current. So in order to observe the growth of the current, so let us try to consider first how the charges, accumulation of charges takes place from 0 to certain maximum value. Okay, so variation of the charge is very important. So that rate of change of the charge will give you indirectly the change of current in the circuit. Correct? Okay, now so what is the potential drop across the resistor then? So as I told, VR is equal to I into R. So with respect to this current across this resistor, so the potential drop is equal to only I into R. Okay, then similarly the potential drop across the capacitor, so that is depending upon the capacity of the capacitor, right? So VC, potential drop across the capacitor is VC is equal to Q by C, where Q is the charges present in the capacitor already at a given instant of time. Okay, where C is the capacity, it is a constant capacity of the capacitor. So Q by C ratio will give the PD across the capacitor, and I into R gives the PD across the resistor. Clear? Okay, now follow the Kirchhoff's voltage law. So according to Kirchhoff's voltage law, we have the total EMF present in the loop is equal to E. So that must be equal to the algebraic sum of the potential drop across the R, potential drop across the C, both you have to consider, right? So add these two, Q by C plus IR. Okay, so that must be equal to the total EMF present in the circuit. Supply EMF is E. So that is the equation you will get. So now let us continue. Because we know that the current is given by rate of change of charges here. So dq by dt. So since I is equal to dq by dt, you just make the substitution of that here. E is equal to Q by C plus this dq by dt into R. Right? R is there here. Now just go on simplify this equation here. How do you simplify, you know? So first you have to divide by R. On both sides you just divide by R. So E by R is equal to Q by RC plus this dq by dt into R is there, isn't it? So this R cancels here. This part R cancels when you divide by R on both sides. Okay. Now in this equation, just you have to do some rearrangement of the equation. dq by dt is equal to, see, take this term dq by dt at left hand side. So that is equal to E by R minus Q by RC. Right. So we have LCM now. What is LCM for this R and RC? RC is the LCM. Okay. So if you take RC as LCM, here in the numerator you have to multiply by C. So that is E into C. Here RC is there already. So just write as it is, minus Q only. So EC minus Q divided by RC will get the form of an equation for dq by dt. Okay. Let it be equation number 3. So then I will proceed it for the simplification in the left hand side now. Okay. So note down all these terms up to this equation 3 first. So continuation of the equation 3 is here. So where the rearrangement of the equation is done like this, dq by EC minus Q, okay, from that equation 3, and is equal to dt by RC. So that means we are making all the charges terms, Q terms at one side and time at the other side. So that you can simplify by integrating the equation. Okay. So integrating the equation means integrate on both sides, like integration of dq by EC minus Q is equal to integration of dt by RC. And you know integration is very simple here. So with respect to Q, so we can get the integration of the denominator EC minus Q. Okay. So because variable is Q here, so we'll get the negative sign here. So minus. So log of EC minus Q is equal to RC is constant. So integration of dt is equal to T only. So therefore T divided by RC plus K. So what is this K? Integration constant. Okay. So we can find the constant of integration by applying the initial conditions, right? So what are the initial conditions? So at time t equal to 0, so we assume that the charges are 0 in the capacitor. So therefore t equal to 0, so it tends to be q equal to 0 in the capacitor. So therefore the equation 4, so just substitute the conditions t equal to 0, q equal to 0 in the equation 4 only. So that you will get minus log EC. So this q equal to 0 is equal to this t is also 0, you will get only k. So value of k is equal to now minus log EC. Okay. Substitute this value of k again in the equation 4, so that the equation 4 becomes now minus log EC minus q is equal to t divided by RC minus log of EC. So value of k is substituted here. Clear? Okay. Just now further steps are all only mathematical simplifications for you. So that is you just rearrange the terms so that you take all log terms at one side now. So minus log is there, so you just take the minus log of EC minus Q in the right hand side. So you get log EC minus Q, okay, and here already minus is there here, so minus log EC. Okay. So T by RC you have to take in the left hand side, you know, so that is what actually we can write here. So minus T by RC plus becomes minus here. Okay. In the next step, so it is just like log A minus log B. Okay. So you are applying the identity log A minus log B. So therefore you can write log of EC minus Q divided by this EC. Okay. So all terms are actually logarithmic terms with base E. Okay. So that you can eliminate the log now. So on left hand side, so that you will get the EC minus Q by EC is equal to, so this E is there, no? So base E, log of base E. So that the entire term minus T by RC will become the exponential term. So e to the power of minus t by RC when you eliminate the log in the left hand side. Clear? Okay. So now simplification is just divide by EC, both the terms here. So EC by EC, so is equal to 1, and then Q by EC, so is equal to minus T by RC. Clear? Okay, again rearrangement is, so Q by EC is equal to, you take this Q by EC in the right hand side, let us say. So 1 minus this term, he has to take it in the left hand side. So 1 minus e to the power of minus T by RC. Okay, by cross multiplication you can write Q is equal to EC into 1 minus e to the power of minus T by RC. Okay, so that means we are getting the expression for Q here as Q is equal to EC into 1 minus e to the power of minus T by RC. So of course, what is this EC, you know, according to the condition of the charges in charging of the capacitor, C is equal to, so that is EC, product of EC. By cross multiplication actually it is Q naught only, right? So that means if EC is equal to Q means what? You will understand C is equal to Q by E. So that is the principle of the capacitor already you have taken. Okay. So to the capacity of the capacitor it can charge to the applied potential E. Okay, that is why. So product EC is equal to, now you can write it as Q naught, because Q naught is the maximum charge you can understand in the capacitor. Okay. So now this equation Q is equal to Q naught into 1 minus e to the power of minus T by RC indicates how the charge in the capacitor is going to be increased with the increase of time t. Okay, because it is charging growth. Okay, so the growth of the charges takes place in the capacitor with respect to time t. So what about the current? Okay, if the charges in the capacitor increases, then the charging current is actually decreasing. Okay, to see that equation, what you have to do? You have to differentiate the equation Q with respect to time t, isn't it? So that's what I have done here. So in terms of charging current, equation 5 can be written like this: I is equal to dq by dt. Differentiate the equation of Q, dq by dt, that is equal to d by dt of Q naught into 1 minus e to the power of minus T by RC, right? So again differentiation means you have to write now Q naught, differentiation of this entire term will get actually minus and minus plus 1 by RC. So Q naught by only RC. Clear? So Q naught is there already, so by 1 by RC. So it is equal to Q naught by RC into e to the power of minus T by RC. So here you can write Q naught by RC is equal to what? I naught. That maximum current, depending upon the maximum charge, so maximum current is there. Okay. So I is equal to I naught into e to the power of minus T by RC. So now both are exponential term. Okay, that means Q is also an exponential equation, I is also an exponential equation. So then if you plot the graph of the variation of the charge in the capacitor Q with respect to time, as per this equation you can understand that actually the Q is increasing, exponentially increasing, whereas the corresponding current, the charging current decreasing, exponentially decreasing again. Okay. Now let us see with respect to these equations 5 and 6, okay, how we can understand the growth of the charge in the capacitor during charging of the capacitor in RC circuit. Okay. Okay. Here you look at the graph, growth of charge on the capacitor. So as per the equation 5, okay, so that mathematical equation confirms that the charge in the capacitor is increasing exponentially. Okay, that is a mathematical expression. And then the same thing you can obtain experimentally and prove that how the charge is increasing. Charge is taken in terms of coulombs with respect to time t in seconds. Okay, so this is the curve you will get experimentally. That means it is the exponential growth of the charge in the capacitor, okay, during charging of the capacitor, right? So in that maximum charge is accumulated in the capacitor is how much? Q naught. Okay, it is the maximum value. Okay, till it reaches the maximum value. So the time period is called actually the transient time period, isn't it? So delta t is the transient time period. So during the transient time period, the growth of the charge is exponential. Clear? Now with the help of the same graph, we can understand the time constant also in the RC circuit. Correct? So time constant is denoted by tau. So the quantity RC in the equation 5, the quantity RC is the time constant of the RC circuit here. So that you can substitute now tau is equal to RC seconds in the equation 5. Okay, so you take time t is equal to tau equal to RC in the equation 5. So that you can substitute now Q is equal to Q naught 1 minus e to the power of minus RC by RC. So that you can just cancel this RC, time constant RC cancels each other. So left with 1 minus e to the power of minus 1 or 1 by e. Okay, e value is 2.718. So reciprocal of 2.718 is equal to 0.368. So 1 minus 0.368 is equal to 0.632. So 0.632 times of Q naught. What is Q naught? Q naught is the maximum charge in the capacitor. So hence you can say, so in terms of percentage, it is 63.2% of the maximum charge. So you can define now what is the time constant, RC. So the time constant of a RC circuit is defined as the time taken by the capacitor to acquire 63.2% of its maximum charge. Clear? See, you can look at the graph also. If Q naught is the maximum, then here is the 0 exactly at time t equal to RC. Okay, so t equal to RC is the time constant. At this particular time, what is the charge accumulated in the capacitor? It is not maximum, isn't it? It is just 63.2% of Q naught. So hence you will get the value here. Okay, so 0.632 times of Q naught or 63.2% of Q naught, you can say, at the time constant value. Further, as the time lapses, almost 5 times of RC, time will make the charge to accumulate the maximum value. Okay, so that is all about the growth of charge in a RC circuit. Okay, so the next video I will consider the decay of charge in the RC circuit. That means when the switch is turned off across the RC combination, how the accumulated charge in the capacitor decreases in the transient period again. Okay, so in the transient period only you have to estimate the growth or decay of charge in the capacitors. Okay, not the current. Okay, if you take the current, what happens? As I told, the charging current actually decreases exponentially here. Okay, it is decreasing exponentially like this. The charge is increasing and hence it is called growth of charge. Clear? Okay, I will see you in the next video with the concept of decay of charge in the RC circuit then. Okay, okay, see you in the next video then.